Hi, this is going to be a lecture on chapter 6, and I'm going to share the screen. And I'm also going to tell you, I'm not sure if this will turn out to be a video that's divided into two, or whether I can finish it all in one setting. It just depends. I'm not quite sure of the speed of it. It's going to be around an hour. It might be a little bit more, and I might divide it into two. Either which way, it'll be in the same module. I'm not dividing it between 2 weeks. I'm just dividing it so I can take a little break. That would be all. All right, so we're dealing with the motor control for speech production in this chapter 6. And you're going to recognize some of the material from the last part of chapter 3. When we went into they labeled it the principles of the ipsilateral and contralateral control of motor speech production. And I think that they weren't trying to give all the details there. They were simply trying to introduce you to the idea of contralateral and ipsilateral control of the speech production mechanism. And also we looked at the body. Well, this just goes into a little more detail. So we're going to go through several slides that will look quite familiar. I mean, I think some of them are exactly the same, but they do add some information and reinforce what you've already learned. And we're going to look first at what's called the pyramidal system. I'm not sure that that is familiar to you, but when we were looking at those cortical spinal neurons that ran from the motor cortex down to the lower motor neuron, which went out to the striated muscles and innervated them, that's referred to as the pyramidal motor system. It is responsible for voluntary control of movement. We're also in this set of slides toward the end, but actually it's more than just the end, it's about 2/3, I think. We're going to look at a different, newer system, new to you, called the extrapyramidal system. And that is superimposed on the pyramidal system in this way. It refines the movement, it coordinates movement, it provides muscle tone, it coordinates or moderates what is called the stretch reflex, and I'll get into that. But we're going to be dealing first with the pyramidal system and second with the extrapyramidal system. And then you will be pretty familiar with the motor system throughout the body, familiar enough anyway, and I think we'll be moving on to other things in subsequent chapters. Okay, so first of all, we're going to review a trunk and limb movement, and this would be pyramidal system, but we've been using the term cortical spinal, and I'll point to that right here. Voluntary trunk and limb movement is observed by the cortical spinal tract, which is a tract of axons in the brain. They originate in Brodmann's area 4. You knew that. Those axons, which can be quite long, travel down through the internal capsule, down through the cerebral peduncles of the midbrain, down through the pons, and then the medulla. And then when they get to the caudal medulla, 90% of them decussate to form the lateral cortical spinal tract, which you find in the cord. It's out in the lateral funiculus. 10% of them, or so, I think I might have said 15%, but roughly 10 to 15% do not decussate. And they continue on down the same side they originated, and they form the ventral cortical spinal tract in the ventral funiculus of the spinal cord. Neurons in both the lateral and the ventral cortical spinal tract tracks then synapse on the lower motor neurons, which have several names. Alpha motor neuron, they're called often. The final common pathway to kind of give the idea that those alpha motor neurons get a variety of input from the pyramidal system and from the extrapyramidal. And those neurons then sort of take the information that they have, which would be in the form of EPSPs and IPSPs, remember those, integrate it and send out a specific message to a muscle to contract X amount in those 31 pairs of spinal nerves. All right, and you've seen this one before. It shows the anatomy that I just went through from a different perspective, showing the array of neurons that start in the motor homunculus. And as you know, lower extremity down here, body, great big face, great big hand, and 90% of those go down and decussate at the caudal medulla. They all synapse then on alpha motor neurons, And this illustration just shows the decussation of the cortical bulbar tract. It also shows, in a kind of a rough way, the decussation of the cortical nuclear or cortical bulbar tract. I think I misspoke. It shows the decussation of the cortical spinal tract here at the caudal medulla. And then the cortical bulbar tract, which is right in there with the cortical spinal, decussates at all different levels where they are going, where these neurons, these upper motor neurons, are going to synapse with a lower motor neuron, such as, for example, the facial nucleus, which is going to go out and innervate muscles of facial expression, etc. All right, this is another depiction of that pattern of decussation. The cortical spinal tract decussates partially at the caudal medulla, as you know, shown in the previous slides. The neurons that make up the cortical bulbar or cortical nuclear tract decussate at the level of the brainstem nucleus, in which they synapse on a lower motor neuron. All right, now, what nuclei are we talking about that have motor functions? Well, this shows 3, 4, and 6, the nuclei that innervate the extraocular muscles, and they move your eyes. 5 and 7, very involved with speech, of course. Trigeminal, motor nucleus. Here, in this case, we're talking all motor, and the facial nucleus. And then down here in the medulla, they're referring to cranial nerves, but the cranial nerve here would be the nucleus ambiguous. And then the 12th is the hypoglossal nerve, the nucleus, the hypoglossal nucleus. Okay, so those are the motor nuclei of the brainstem that receive input that we refer to as cortical bulbar or cortical nuclear, and some of those neurons decussate. Now, the exact percent of neurons that decussate at each level differ depending on the part of the body receiving the input, and that applies to the cranial nerves as well. So we're going to look at that in a little more detail. You have seen this table that shows the pattern of decussation before. We looked at it it was one of the last parts of chapter 3. I think I've added some detail. I don't remember whether I put this part in there before, but the rest of it you've seen. You know that overall, 85 or 90% of the upper motor neurons that we refer to as cortical spinal do decussate, 10 or 15% do not. The precise number does not matter, but you get the idea that overwhelmingly most of them decussate. All right, then when we go down to the extremities, you can see that the upper extremity has a larger percentage of upper motor neurons that decussate than does the lower extremity, 85 versus 75. You can also see that distal parts of the extremity have a greater number of percentage of decussated neurons than do the more proximal parts, and that applies to the upper extremity. Here we have a 95 versus 75, and the lower extremity, 85 versus 65. All right, now for the trunk, the neck, the pharynx, the larynx, that's intrinsic larynx, I should say, not the strap muscles, but the intrinsic muscles of the larynx, the velum, and the upper 1/3 of the face. The crossing is about 50-50. So you're going to think of those conceptually, even though they're different parts of the body, conceptually in terms of the pattern of cortical spinal / cortical bulbar input. You're going to link those in with the trunk and the neck. When I think back here to the larynx and what I just said, I said intrinsic muscles, but it also applies to the strap muscles, which are, after all, part of your neck. What's different? The lower 2/3 of the face and the tongue, lower 2/3 of the face and the tongue receive mostly contralateral cortical bulbar input. You think of those more in the conceptual category of the extremities. The extremities get most of their cortical spinal input from the opposite side of the brain. The lower 2/3 of the face and the tongue get most of the cortical bulbar input from the opposite side of the brain. All right, so this is a very important table, not to so much memorize the exact numbers, but certainly to see the pattern and understand and integrate the pattern into your understanding of the neurological system. All right, I do believe we also saw this once before, but it's worthwhile reviewing. It shows the lower motor neurons of the facial nerve that are destined for the upper third of the face, receiving input about equal from both sides of the brain, from both motor strips. Whereas the lower motor neuron of the facial nerve receives input primarily from the opposite side. Now, let's take a look at that. Here we see a neuron going to the lower 2/3. That's what they're trying to show here. And if we come back here, and look at the origin of that, we can see that it receives input mostly from the opposite side. You see they're showing this neuron from the cortical spinal, from the motor strip going here and synapsing there, but they're not showing one coming from the opposite side. You have to really look in detail at this. Whereas when you look at the neuron, the lower motor neuron that's going to the upper third of the face, note it's receiving input from the opposite side, and it's receiving input from the ipsilateral side. So that gives it the protection. If you have a lesion up here, the upper third of the face is protected. The lower 2/3 of the face is not. So that's where you'll see the weakness. All right, let's go on to the next one. Now, the clinical implications of the difference in the percent of across cortical spinal neurons for different regions of the body. And you've seen this before, but this is so important. It's good to go. I'm glad they introduced it in 2 chapters or went over it again. When the damage of the cortical spinal or cortical bulbar fibers is above the level of the decussation, the impairments are on the opposite side from the damage. Let me say that again. And this is going to, by the way, this is going to apply to our motor and sensory systems. Now, right here, we're just talking about motor, but the rule, the way I'm articulating it, would apply either way. Take a system, a sensory system for pain and temperature, a sensory system for fine touch proprioception, and talk about the relationship between the location of the damage or the side of the damage, brain damage, where the decussation is and where the impairment's going to be, or the side of the impairment. If the damage is above the decussation of a system, the impairment will be on the opposite side. If the damage is below the decussation of a system, the impairment will be on the ipsilateral side, the same side as the damage. This also will predict knowing the pattern of decussation will predict the recovery pattern. And we had gone over this before. When you look at somebody whose damage is above the decussation, and let's just take the body for example, for right now, let's forget about the face for a moment. Put the damage above the decussation of the pyramids. The worst paralysis will be on the opposite side from the damage, and it will be the hand. The foot, not quite as much. If you test the wrist, probably not very much movement. If you test the elbow, a little bit of movement. Test the shoulder, little more movement. Test the trunk, okay. Neck, okay. Then when you look at the pattern of recovery, you see movement around the shoulder will come back first. It'll always be a little bit ahead. It's going to go however far it goes. In other words, they may not necessarily have a complete recovery at all, but the shoulder is going to be a little better. The elbow, the movement around the elbow, not as much. Wrist, not as much. Fingers, they may never get back. So knowing this information predicts and tells you why the weakness at the initial phase is what it is, how that pattern, why the pattern is what it is, and it will also predict the pattern of recovery. All right, I think I skipped one here. Okay, now we get into a definition for the pyramidal system and the extrapyramidal system. So this is just a kind of an overview. The pyramidal system is a system of upper motor neurons that provide input directly from the motor cortex to the lower motor neurons. Now, the idea is direct. There's nothing in between. It doesn't synapse on anything. It doesn't process any more information in some nucleus or something. It just goes right from the motor cortex right down to an alpha motor neuron and out to a muscle. It's a 2-neuron chain. Doesn't matter if you're talking about a cortical spinal neuron that goes all the way from the cortex down to L5 or S5, way down at the bottom, or whether it comes up to a cranial nerve. It's going to be the same. It's a 2-neuron chain. The extrapyramidal system is a system of upper motor neurons as well, and they provide input indirectly. In other words, they don't go directly down to an alpha motor neuron. There's something in between where some information gets processed. And they end up all going to a gamma motor neuron, which is down at the level of same level as an alpha motor neuron. In other words, if you're down at the spinal cord, the gamma motor neurons and the alpha motor neurons both go out to the ventral root, remember the ventral root, spinal nerve, and out to the muscle. Now, they're going to do slightly different things. The alpha motor neuron is going to give it a command, which you could think of as, in a way, an easier command or a simple command. The gamma motor neuron is going to be involved in a more complex process to coordinate the movement, to regulate the muscle tone, the posture, the reflexes, and we'll get into what those are exactly and begin to make a little more sense. Okay, did I skip something? I did, yeah, good thing. Now, I've used these terms before, but I want to give a more formal definition: upper and lower motor neurons. Upper motor neurons are neurons that connect the cortical motor areas of the brain directly or indirectly with lower motor neurons that are found within cranial nerves and spinal nerves. Okay, now what are the lower motor neurons? The alpha motor neurons and the gamma motor neurons. Anything that provides input to that would be an upper motor neuron. Now, the one thing that you have a lot of knowledge about right now is the cortical spinal neurons. Those are upper motor neurons. They provide input to the alpha motor neuron. You also know about the cortical bulbar, which are exactly the same thing but they don't go down to the spinal cord level. They go down to the brainstem and innervate a cranial nerve. The lower motor neurons are neurons that have cell bodies within the CNS. If you're talking about the spinal cord, it would be the ventral horn of the spinal cord, or the cell bodies are in the cranial nerve motor nuclei, if you're talking about brainstem and cranial nerves. And these lower motor neurons terminate on striated muscles. It does include, lower motor neurons include alpha motor neurons, beta motor neurons, which we're not going to go into, and gamma motor neurons. We'll have a complete understanding of the pattern of deficits and impairments that our patients have if we only deal with the alpha motor neurons and gamma motor neurons. So that's all we're going to do. And that'll be enough, I'm sure. All right. The pyramidal system is a system of upper motor neurons that subserve voluntary movements. They consist of, now this should be kind of a review for you at this point, the cortical spinal tract and the cortical bulbar tract. Webb indicates that something called the cortical pontine tract is part of the pyramidal system, but I cannot find any reference that includes this. This tract is responsible for input regarding voluntary motor commands to the cerebellum, which in turn is responsible for coordinating movements. Now, we will talk about coordinating movements, but it's kind of a minor point, even though I've consumed 8 lines to talk about it. I think it's an error in the book. Actually, the cortical pontine tract cannot, in anything that I can find, is not part of the pyramidal system. It's part of the extrapyramidal system, actually. Okay. All right. The extrapyramidal system is a system of upper motor neurons that provide input to the lower motor neurons for the purpose of regulating reflexes, muscle tone, and posture. And these are the ones that we're going to study. We're going to study the cortical reticular tract, which provides input to the pontine and medullary reticular formation from the motor or area of the cortex down to the reticular formation. That's kind of a new term for you, but we'll get into it. Provides input to the reticular formation of the pons and the medulla. Then, lower than that, cortical reticular tract is up in the brain. Lateral reticulospinal tract and medial reticulospinal tract run from the pons and from the medulla to lower areas. Could be all the way down the corridor, could be a lower area for a for a cranial nerve, excuse me. The lateral reticulospinal tract inhibits muscle tone and the stretch reflex. Now, I'm going to just leave that right now and pick it up and explain exactly what that means. But for right now, I want you to tune in on the word inhibits. The lateral reticulospinal tract is inhibitory. The medial reticulospinal tract is excitatory. So if we're talking about something like muscle tone, just as you sit there, you've got muscle tone. Every one of the muscles in your body has some background level of contraction going on. It's not completely flaccid. Flaccid means there's nothing happening there. You don't have any muscles that are completely flaccid unless you have a peripheral nerve lesion or some other kind of a neurological problem or neuromuscular problem. So we have muscle tone. Just as I sit here, the way I'm staying upright is really not to be thinking about sending a certain amount of input down to all my postural muscles. There's muscle tone in them, and they're kind of preset just to be like this so I can stay upright without a whole lot of mental activity. And that is representing some kind of a balance between inhibition and excitation. For example, if I just got very tense, or you got very tense, your muscle tone would increase. That's why we get neck aches and stuff. That means there'd be more going on here, more excitation in the medial reticulospinal tract, which is excitatory. So for right now and for this slide, associate lateral reticulospinal tract with inhibition of muscle tone and the stretch reflex, the medial reticulospinal tract with excitation of muscle tone and the stretch reflex. The vestibulospinal tract originates in, you might guess, the vestibular nuclei. And it is involved in maintaining body's balance at a reflex level. In other words, if you trip on something, the information, and you start to fall, the information that feed back to your brain doesn't have to go all the way up to the cortex where you realize, I tripped, I better make an adjustment. It's a reflex. It only gets up to the vestibular nuclei, and they start sending messages down to your body in a certain pattern to right yourself, to bring yourself back up to where you were instead of falling on your face. It's kind of cool. It saves time and it prevents you from actually falling. At least some of the time you may complete the fall, but it's the vestibulospinal tract modulates a reflex to keep us in the position that we want to be in. And then the rubrospinal tract originates from the red nucleus, and it provides input from the cerebellum to coordinate movement. So again, coordination. Now, we're going to do quite a bit on these three. And these, we're not going to go into details of the anatomy, simply to know their function and that these things are going on at a reflexive level and an automatic level. In other words, we don't have to think. If you simply want to, if you want to bring your finger to your nose or anything, any kind of movement, it's hopefully going to be pretty smooth. If you don't have a cerebellar injury or dysfunction, it will be quite smooth. But it takes a lot of coordination, as you can imagine, to produce that smooth movement. And as we initiate commands to go down to our muscles from our motor cortex voluntarily, we think about it, I want to do this, you don't send the complete information down there. You basically just say, I want you to go through space like this. And all the coordination of the agonist and antagonistic muscles required to get there smoothly, let's do that automatically down at a lower level of the brain and not take up the power of the cortex. So that's what is going on here. And that's about all we're really going to say about the vestibulospinal and the vestibulospinal and rubrospinal tract is sort of their function and their location. And so you begin to understand that our movements are modified and smoothed out, coordinated, and become reflexive with these brainstem mechanisms. Okay, now a little more about those three that I said we were going to go into, because they're so important for the understanding of the pattern of weaknesses and problems that people get with brain injury at different levels of the system. So I want to do that quite a lot, or give you enough information so you really understand. And I can jump ahead for a moment and say, basically, you're going to see people who have weaknesses and they can't move their muscles well, or maybe not at all. And you're going to see them in two categories. Those who have a flaccid paralysis or paresis, meaning they're just plain weak and their muscle tone is reduced as well. And those who have a spastic paralysis or paresis. Now, when I say paralysis, it means they cannot voluntarily move their muscle. But when you look at that limb that's in this, often it's in this position, and every muscle in it is completely tight. They have, in other words, elevated muscle tone. And they have what's called spasticity, and it can be very severe. So they have elevated muscle tone. They're getting messages to the muscle, but not in a way which allows them to do work with it, which means they're paralyzed. They have spastic paralysis. So I want you to understand the difference between the two. First of all, how to identify them. You'll be able to identify them and understand where in the system the damage would have to be in order to produce either a spastic or a flaccid paralysis. When you see a muscle that has a flaccid paralysis, you know right away it is in the peripheral nervous system that the damage is located. It is either the nerve itself, or it could be a root. It's a root or a nerve, or it's the nucleus, which is actually in the CNS. But when you knock out a nucleus, a motor nucleus, such as a facial motor nucleus, you're knocking out a lower motor neuron. It would be the same as snipping the nerve, even though the damage itself is in the PNS. It's about the neuron, in other words, and you can damage that neuron by taking out the nucleus, which is in the CNS, or you can damage the neuron by going out to the periphery and snipping the nerve. Okay, so we're going to be looking at these three: the cortical reticular tract, and the lateral reticulospinal tract, and the medial reticulospinal tract. Okay, going up here, cortical reticulospinal tract, it originates in the motor strip and in some other motor areas of the cortex. So it's not strictly the motor strip, but it's pretty close to it. And it generates EPSPs in both the pontine and the medullary reticular formation. The lateral reticulospinal tract participates in the generation of muscle tone and the stretch reflex, which we'll define later. It originates in the medullary reticular formation, and it generates IPSPs, or the neurons in it generate IPSPs on we'll get to know in a few minutes, a gamma motor neuron, which is a lower motor neuron, but a different type from the alpha motor neuron. And I asked the question, activity in these neurons would change muscle tone and the stretch reflex in which direction? Well, the answer is it would reduce it because it's inhibitory. The medial reticulospinal tract participates in generation of muscle tone and stretch reflex as well. So you see, this first 2 points are the same. It originates in the pontine reticular formation. Hence, it's not, the pontine is not in the name here. No, you just have to remember it. Lateral reticulospinal starts in the medullary reticular formation. Medial reticulospinal tract starts in the pontine reticular formation, and it generates EPSPs on gamma motor neurons. And I asked the question, activity in these neurons would change muscle tone and the stretch reflex in which direction? It would increase them. Okay,
The vestibulospinal tract, just a little more detail in writing here, facilitates reflex activity and spinal mechanisms for controlling muscle tone for body position in response to gravity and acceleration forces. So this tract is receiving input from your vestibular cochlear about the direction your body's moving, how fast it's moving, and what angle you're at. And it will do corrections for that then. And send actually it'll send motor impulses down to gamma motor neurons and start correcting things in response to input that has been received by your balance system, basically at the brainstem level. The cerebrospinal tract transmits coordinated input from the cerebellum to lower motor neurons. All right. Now, we're going to focus on the neurophysiology of muscle tone and the stretch reflex. And this is required in order to understand how upper motor neuron injury results in spasticity. This is a key point. I want to point that out. Upper motor neuron injury results in spasticity, whereas lower motor neuron injury results in flexity. What characterizes spasticity? Reduced muscle strength, elevated muscle tone, and what is called a hyperactive stretch reflex. We'll get into that. But one way of measuring the hyperactive stretch reflex, or a stretch reflex, is the traditional tap by the neurologist with a little hammer, that little B-shaped hammer on the knee. They're tapping a muscle and they're testing that reflex. And normally you have a little bit of you kind of give a little kick when that muscle, that's the patellar muscle, gets tapped. If somebody has spasticity, an upper motor neuron disease or injury, they give a great big kick. They have a hyperactive stretch reflex. And I'll give you more details on that, but just to introduce you to the idea of what a hyperactive stretch reflex would be. Lower motor neuron injury results in flexity. Again, there's reduced muscle strength. Either which way, whether it's spasticity or flexity, the muscle can be paralyzed or it can be weak, which is a paresis rather than paralysis. In this case, there's reduced muscle tone. In the case of spasticity, it's elevated muscle tone. This is reduced muscle tone. And there's a hypoactive stretch reflex, or in the most severe cases, no stretch reflex at all. In other words, the neurologist taps the patellar muscle and that there is no kick. And you can feel it in the muscles too. You can feel, oh, they're completely soft. There's nothing going on there. And they're of course, they're weak. Okay. Now, continuing to focus on the neurophysiology of muscle tone and the stretch reflex. You need to understand this in order to understand speech motor control. Now, this is going to kind of require you to think about it a little bit, and I would suggest that it's probably an area where you want to go back and read this section of the textbook in chapter 6, just to hear it in words other than mine, and read it in words other than mine, to find out what is this all about and how does it impact speech. And I'm not necessarily at this moment talking about disordered speech, even normal speech. This is all operating. So what's happening as you speak is your motor cortex is sending signals down to the lower motor neurons involved in the speaking act to indicate what the articulatory targets should be. If you think about something like a T sound, the articulatory target is for the tip of the tongue to reach the upper alveolar ridge. And so a command's going to go down there, go there and do that. However, exactly how much contraction you need to do of the various tongue muscles in order to reach that target will differ depending on co-articulation. What are the sounds that are surrounding it? It could take a little more push to get there with some sounds that surrounding the T and a little less with others. It's a constant variable. So what your motor cortex is doing through your pyramidal system is simply sending commands down to approximate this target. And then the reflexive mechanisms are kicked in to actually accomplish the smooth muscle movements and the exact amounts of contraction of all the various muscles to get there. There's coordination, which is a cerebellar input. And there is also activity in the reticulospinal, reticulospinal tract, the lateral reticulospinal tract, and the medial reticulospinal tract to exactly coordinate how much contraction is needed. So there is a combination of input from the cortical spinal and cortical bulbar neurons, plus the neurons involved in the stretch reflex to, in effect, push down to the reflex level the many demands of speaking. Let me make sure yeah, okay. So let's go a little deeper into that. What is muscle tone? I've used the term a lot, and I think you're getting an idea about it. It's a background level of muscular contraction present in all muscles at all times, and it functions to support posture without requirements for involvement of the motor cortex. In other words, as I sit here, I gave the example of just sitting here. I'm not sending a whole bunch of commands down through my pyramidal system to maintain this posture. It's pretty automatic. The stretch reflex, which also is called the myotactic reflex, is defined as a muscle contraction in response to stretching within a muscle. Okay, now what exactly does that mean? Well, let's go into it. A monosynaptic reflex is which provides automatic regulation of skeletal muscle strength. That is a stretch reflex. Monosynaptic means there's one synapse in this little reflex loop that accomplishes the stretch reflex. And we'll look at exactly the anatomy of that in a moment. Let me try to explain what these last two points there, what the stretch reflex is doing for us. I mentioned sending targets to muscles to approximate a certain amount of points. Now let's just say, for example, that you're going to send muscle commands down through the pyramidal tract to pick up a load. It could be a feather, it could be a glass of water. Let's take a glass of water, and let's say it's it's a glass of water. You don't know exactly how much to contract each muscle in order to bring that glass of water smoothly up to your lips. You know the targets you want to achieve. You know you want to go from this point down here up through here. And you want that movement regardless how heavy that water turns out to be. And you won't really know till you pick it up, right? And you may think, well, it's a glass of water. How much could it vary? If you start generating forces with all your muscles that would pick up a glass of water twice as heavy as another glass of water, you're going to have movements that are twice as intense, and it's not going to work out. It's got to be precise, and you won't know until you start to pick it up. So you might think, well, that information, you start to pick it up and go back up here and you process and you figure it out. It's not like that. You don't figure it out at all. All your cortex is going to do is say, I want to go from down here on the table with this glass of water up to here, and I want somebody else down there at lower levels to figure out exactly how much force to apply to each muscle, or how much to contract each muscle, twice as much as. It's not going to work. It's got to be exact. So the stretch reflex actually accomplishes this. You go down, you start to pick up the water, and you think you're supposed to be, a half an inch up from the table now, but it turns out the water's heavy. And what happens is the muscles that were to bring it up 1 inch actually get stretched. You can kind of imagine this if you think about an extreme load. If you go out to pick up a bucket of, I don't know, cement or something, and you think, okay, I can do that. And you start to pick it up. If you're actually going to wear your muscles out because they're going to be trying so hard. In other words, to pick up that heavy, it takes a lot more muscular contraction. And that kind of variability in the exact amount of muscular contraction is in every single movement we make. Every single movement we make, all we're going to send from the motor cortex is, I want you to go from here to here, or I want you to go from here to here, or whatever it is. I want you to take this step. And they all need to be adjusted in order to accommodate to the exact situation in terms of weights and forces on those muscles. Same thing for articulation. Okay, now I'm going to take a little break here and come back in a moment.